Hey, Charles.
Hey, Michael.
We're going to talk about exploration.
All right. I like exploration.
Yeah, it turns out to be a really important property or topic in reinforcement learning. I think there are some people who have said exploration is the topic that separates reinforcement learning from other kinds of machine learning. So it's kind of the thing that's special to us.
Yeah, I mean, I think I would argue it's part of a fundamental trade-off of reinforcement learning.
Okay, I'll tell you who said it. It was me.
Fair enough, Michael.
Let's dive in and see what some of the subtopics are. So ultimately, we're going to work our way up to regular old stochastic MDPs and what it means to do exploration and learning in those settings. But by way of warm-up, we're going to look at two other classes that illustrate other aspects of it. We're going to talk about bandits that don't have any state transitions at all.
Okay.
And we're going to talk about deterministic MDPs, which have state transitions but don't have any stochasticity at all.
Okay. But the bandits do have stochasticity?
Bandits are all about the stochasticity, yeah.
Okay.
And so once we've kind of mastered those two, it's kind of combining the union of those that gives us the ability to handle general MDPs.
Combining the union?
Taking the union of the topics and then integrating them into a algorithmic whole.
Sounds promising.
So are you familiar with K-armed bandits?
Let's pretend I'm not.
All right. So let me tell you a little bit about K-armed bandits then. So here's the basic idea. You have K bandits, and each of them has an arm.
So wait, why isn't it K armed bandits then? Why isn't the dash between armed and bandits?
Oh, K armed bandits. Yeah, because each one is an armed bandit, and there's K of them.
Right.
Yeah, that works. But I think we're supposed to think of it as the important thing is that there's K different arms.
Okay.
And so the bandit, this comes from terminology having to do with slot machines. They named this model back in the, I'm going to say 50s. So, we don't have to necessarily understand it anymore. That was ancient history. But the fact of the matter is that sometimes people will call a slot machine a one-armed bandit. And in a slot machine, you get to make a choice at each moment in time which of the one arms to pull, which of course is not a very interesting decision problem. So the idea of a K-armed bandit is you've actually got, in this case, K is 7, and each of these arms has some probability of paying off. So, you pull on it and you either get a jackpot or you don't get a jackpot. Now, usually in a casino, these would be rather low payoffs. In fact, I think it's not so uncommon in the casino for them to have not even necessarily different payoffs. But here, for this, it's going to be interesting to have each of the arms have a different payoff. Or at least we don't know what the payoffs are. They could be different.
Okay.
So which arm do we want to pull?
The best one?
Yeah, which one is that?
The one that has the best chance of giving you money.
Here, I'll make it easier for you.
Okay.
I'm going to give each of them a name. All right, now which one do you pull?
The letter that has the most money associated with it.
Okay, all right. So I think you're making a valid point, though you're making it in a frustrating way. And that is that we don't know which arm to pull because we don't know what the payoffs are. So if I tell you the payoffs, this problem becomes really easy, right?
Yeah.
We just do argmax, right? Whichever one has the highest payoff, we just choose it all the time. But what makes the K-arm bandit problem interesting is that we don't know the payoffs. Let's say instead what we know is that each one has some probability of giving a payoff. And the payouts are all the same. Let's say they're all 0, 1. And each bandit has some probability of paying off a 1. But we don't know what it is at first. And in fact, if we pull arm A, and it doesn't pay off, does that mean that A is not the best one?
No. I mean, how would we know? We don't know what anything else is.
No. Right. So therefore, we can prove that one arm pull is giving us some information, but not an awful lot. We actually have to combine information across a whole lot of pulls to start to really appreciate what the best thing to do would be.
Okay. So we have to explore.
Yes. Good. Way to connect it back to the topic. So, all right, so let's think about what that problem might actually look like. So I wrote down the observed payoffs for each of these arms. Associated with each one of these arms is the number of times that we've pulled that arm, 10, 20, 40, 5, 10, 20, 40. And of those times that we've pulled it, the number of times that it actually paid off for us. So this arm, we pulled 10 times and we got a payoff of 1. This arm, we pulled 10 times and we got payoffs twice, 2 payoffs. So, between A and E, if we had to choose one, it seems pretty clear that E has been better so far.
Yeah, so far.
Yeah. And let's say between A and D, they both paid off once, but D gave us the payoff after only 5 hits, or in the context of 5 hits, 5 pulls, and A in the context of 10 pulls. So D is a bit better than A as well. So what I'd like us to do is think about 2 different things. One is, given the data that we've gotten so far, which arm has the highest expected payoff? And of all the different arms that we could pull, which of the estimates are we most confident in? All right, I reformatted things a little bit. Mostly I wanted these to be the two boxes, and I wanted you to put the letter of the highest expected payoff arm in this box, and the arm for which your estimate of the expected payoff is most confident in the second box.
Okay, I can do that. I actually think that's pretty straightforward.
I don't mean anything super duper technical about this. I just want sort of intuitively what do we have the most confidence in our estimate on? Okay, you ready?
Okay, so one last, just to verify, I'm supposed to be putting in each of those two boxes a letter.
A letter. All right, Charles, what do you think I was looking for on this one?
Okay, so highest expected payoff, well, that's pretty easy in this case because they all have the same payoff of maximum payoff of 1 and minimum payoff of 0. So I really just want the one that has the highest probability of coming up with a 1. And you did me a really cool favor of making each denominator easily divisible by its numerator. So I could rattle off the probabilities of each of those, and they are 1/10, 1/10, 1/10, 1/5, 1/5, 1/5, and 1/5. So 1/5 is bigger than 1/10, so I could put anything of D, E, F, or G in the first box.
Good, okay. So that was in some sense not that interesting. Because it also so if you had put G, just because 8 is bigger than all the other things, that would have been a right answer, but not for the right reason.
That's right.
So you really do want to compute what those ratios are.
Right, and speaking of for the right reason, I think that's what your question about most confident sort of comes from. And I'm just simply going to claim, without writing equations, that when it comes to understanding expectations, your confidence is a, monotonically increasing function of the number of samples. So whichever has the biggest denominator should be the thing that I'm most confident in, because that means I've seen the most samples. So that would be C and G, either of them.
Yeah, okay. And in particular, I wanted you to think about this fact that, so A and C, even though they have the same expected payoff, seeing 1 out of 10, our estimate of what the actual payoff here is going to be much less certain than if we did it 40 times and saw that it was 4 out of 40. This is going to be a more accurate estimate. And so, as you say, the confidence is going to increase monotonically with the denominator. The more data that we've got, the more we believe our estimate based on the data.
Right. So if I were to combine those two things and I just now had to do a bandit, I guess I would pick G because it has the highest expected payoff and I'm most confident in it.
Well, that would be one thing to do. And let's talk about why that could be problematic. All right. So I took your comment to mean, and don't correct me yet, that when you have multiple bandit arms, you want to choose the one that has the highest confidence.
That's not what I said, but okay.
I said don't correct me yet. So so here we have two bandit arms, A and B, and we've pulled B twice, and we've seen one payout. And we pulled A once, and we didn't see it pay out. So in terms of expected value, B is winning.
Yes, B is winning.
And in terms of confidence, B is winning.
Right.
So what do you think the best thing to do is? Do you think at this point we should just always pick A, always pick B, or maybe something else?
I'm going to go with something else.
All right. So if we didn't have that third option, though, which would you choose?
That depends. How many more times do I get to do this? Well, wait, I'm forced to always choose A or always choose B?
Yes.
I guess I'd always choose B.
Yeah. That actually is not a bad idea. But the fact of the matter is that it's the always is problematic. And the reason you want to do something else is because, well, let me first tell you this because I bothered to compute it, so I might as well share it with you. I did the following calculation. I said if we were to randomly choose the payoff rates for both A and B, and then we pull A once and we pull B twice, if we happen to see no payoffs for A, one payoff for B, how often it is the case that B is the better arm than A?
Okay.
And you were right that from the data that we have at the moment, B is a pretty good guess. And in fact, 70% of the time, B is the better of the two arms. But a full 30% of the time, A is the right arm. So you don't want to just go with B because you're going to be wrong almost a third of the time. A better thing to do is something else. So what's an idea for something else? What's a reasonable thing to do if we've got an arbitrary number of pulls left?
So if we have an arbitrary number, then we might as well talk about what happens after an infinite amount of time. If I had an infinite amount of time, then I know my true expected values for A and B, and so I know which one to pull, right? So another way of saying that is I want to do the thing that gets me more confidence in my expectations.
So based on your suggestion, Charles, I wrote down a couple different something else's that might be tried, and I want you to see if you can figure out if any of these are actually any good. So the idea of maximum likelihood would be to say, okay, well, we should figure out which arm has the highest expected payoff and choose that, but keep revisiting the question. So after you've done the pull, recalculate your expected values again and again. Choose which one has the highest expected value and just keep repeating that. And that way, as new data comes in, we're factoring it into our decision.
And so there'd be a similar argument for maximum confidence?
No. So, well, first of all, I wanted you to kind of say whether or not you thought that was a good idea.
That's a bad idea.
It's not a bad idea, but it's a bad idea.
No, it's a bad idea. So in this case, if I look at A and B, right, who has the maximum likelihood? B.
Right. Well, the maximum, let me say it this way. It's the maximum likelihood estimate.
The maximum likelihood?
Right. So the maximum likelihood estimate for this is 0.5,
Mm-hmm.
and the maximum likelihood estimate for this is 0.
Right.
And so this one has the maximum likelihood estimate.
Right, sure, right. So, but here's the thing. Since A has 0 and B has 0.5, I should choose B. But no matter what happens from now on when I choose B, B's likelihood, B's expectation will always be greater than 0, right?
Yeah.
So, I mean, it will begin to approach 0 after an infinite amount of time. But even if I never see a payoff again, it'll still be something greater than 0.
Right.
Which means I will never, ever look at A.
So what does this strategy actually turn into in this case?
Always B.
Yeah. So that works 70% of the time.
That's true.
But that means 30% of the time you're failing.
Right.
And we can do better than that. We truly can do better than that. All right. So maximum confidence says, okay, now the strategy is whichever one you have the best, estimates for, you should choose that one.
Well, that's a bad idea too.
All right. Why is that?
Because whichever one I start out with having the most confidence in, I'm going to pull that. That means I'll get more data, which means I'll have more confidence.
So what would it do in this case? This would be equivalent to what strategy?
Always B.
Yeah. All right. So this we now have two other ways of saying always B. All right. What about minimum confidence?
So you'll alternate between A and B.
Yes.
Well, you may not. You'll eventually alternate between A and B. I don't know. I guess you do A and then you would immediately have the same amount of confidence. So we have to break ties.
Yeah. So if multiple things have the same minimum confidence, it doesn't matter which one you choose.
Right. Although I guess if I would choose the thing with the maximum likelihood, minimum confidence, or minimum confidence of the maximum likelihood.
Oh, if you break that tie, it doesn't matter. Because what's going to happen is these are all the counts are going to be equal. Then you're going to choose one, and then that one's going to have some additional confidence. The other ones are going to be lower. So you choose one of the ones that are left. You're going to end up going round robin through all of them. So the beginning of each round, you might break the ties in some interesting way. But then the rest of the round, you're going to be going through and getting everybody up to the same denominator.
That's true. But given that at any given time, you might take the bandits away from me, I should always pick the thing with the maximum likelihood to break the tie.
Sure.
But your point is well made, Michael.
All right, thanks. Well, the point in this case is that you could do this minimum confidence thing, and you're going to, over time, get better and better estimates of the payoffs of the two arms. But you're never really going to use that information.
That's true.
Right? So if you're always choosing minimum confidence, you're really just going to be uniformly going through and choosing all the arms. It's not a strategy that's going to beat, either these always A or always B. Well, it's not going to beat always B in particular.
It'll be half the time always A and half the time always B, so to speak. So it'll be 50%.
Something like that.
Actually, it'll just be uniform over all the things you got.
Yeah. So it will never actually be picking the better arm. It'll be, or half the time. I guess half of the pulls in any infinite run will be on the better arm.
Well, 1 out of K.
Sure, if there's K arms. Right. In this case, there's 2 arms, but that's right. Good. All right. So these are something else, and these are not better than always A or always B. So we need a something else, even something or else.
Okay. It's going to be some combination of these things.
It does seem like that ought to help. So in particular, maximum likelihood is not a bad idea. Minimum confidence is also not a terrible idea because it is at least bringing you new data. But you want to somehow balance these two. And what we usually refer to this as the exploitation dilemma.
Ah, yes. This sounds familiar.
Right. So the minimum confidence arm is going to get you better estimates, but the maximum likelihood arm is going to get you more reward, probably.
Right. And in particular, like we argued before, if I've only got one more thing to do, I should pick the thing with the highest expected value.
Yeah. So, okay. So to actually make up a strategy that's going to do well in this game, we kind of have to decide what we think the right metric is.
Oh.
So it's not so clear yet that there's one obvious metric. I kind of suggested using these checkboxes that what you want to do is eventually always pull the better arm.
Well, yeah, of course that's what you want to do. Eventually.
Well, no.
Eventually.
No.
Okay, well, look, if you know what the better arm is, you should always pull it.
Sure. But the point is that there's a lot of, fun that happens on the way to that point. And so, in fact, I think all the fun happens on the way to that point. So I think we need to kind of talk about what kind of metric makes sense before we figure out which strategy is the best.
Okay, that seems reasonable.
All right, so I've got a long list of these metrics. I'm not sure how many you would naturally think of, but let me list some, and then maybe you can riff with me.
Okay.
So one metric that we could use is, if we have an algorithm, does that algorithm identify the optimal arm in the limit? Like if you ran this infinitely long, would at the end of infinity, you know which arm has the highest payoff? Okay. So that's good.
Yes.
Because it's good to know what the highest arm is, right? But it's kind of bad because this metric is actually achieved quite well by an algorithm that just round robin chooses all the arms. Pull the first one, pull the second one, pull the third one. So in the limit, we'll have all the data that we need to estimate them as accurately as we want, but we'll actually not have taken advantage of it ever.
Right. And so I think it's important to say then, right, that this is like the normal reinforcement learning setting. So while you're learning and doing whatever you're doing, you're still accumulating reward.
Yes.
Or not.
Right. So it would be nice to have a metric that actually paid attention to not just how much we're learning, but how much reward we're getting in the process. So we could just make that the goal.
Sure, but isn't that the original problem? I mean, how do you do that?
No. I mean, we were phrasing the original problem as figuring out which arm has the highest payoff.
Okay.
So this is kind of different than that, right? This is maximizing the discounted expected reward, which is going to, to do that well, you should do some amount of exploration, but also some amount of exploitation. You're getting reward, but you also need opportunities to get high reward by identifying high-scoring arms.
Yeah, sure. That makes sense.
Okay. So this is totally doable, except it's not so doable in that it ends up being, the computation for this ends up being somewhat intractable.
Oh, of course.
We could talk about how you can actually do this in practice. There's some special cases that actually work out beautifully. There's a thing called a Gittins index. So Gittins index is a way of saying, all right, here's an arm, and I've pulled it, some number of times in the denominator, and I've gotten some number of successes. These two numbers can be mapped to a value called the index, such that if you do that for all the arms, compute all their indices, and always take the maximum one, you actually maximize discounted expected reward. So it's this really clever mapping from the number of successes and the number of pulls to a number such that always greedily choosing with respect to that number is optimal.
What is the Gittins index?
What is the Gittins index? I think it comes down to, if I gave you the choice between this arm and something with a known payoff, how high would that known payoff have to be for you to forego ever trying the uncertain arm? So it's basically how, if I could pay you off and say, you're never allowed to choose this bandit again, how much money would you expect for me to do that? Or what expected value of a payoff would you need so that you don't even ever need to try this again? And so it ends up being greater than the expected value of the arm itself, right? So if the arm has paid off 0.2 on average, but we've only tried it 20 times, then this index value is going to be bigger than 0.2. It's because I wouldn't be willing to just take a sure thing of 0.2 instead of this one, because I could pull this a couple times, discover that it's actually higher paying, and do better than the 0.2.
So somehow the index has to compute some kind of confidence on the probability that this is higher or lower than the expected value or something by some amount.
Yeah, and so it actually ultimately combines this notion of the maximum likelihood and the low confidence, right? So if you have low confidence, then you get an extra bonus for pulling this arm because it may reveal something really valuable.
Right. Okay. So there's magic you can do that computes this and stuff happens.
Right. And so I want to caution you, though, is the Gittins index is extremely seductive.
Yeah.
In that it's this beautiful idea that works incredibly well for bandit problems and feels like it should generalize. And people have not been able to generalize it, but they've wasted a lot of time trying to. So I would caution you, don't go down this road. Unless you think you have a fundamentally new way of doing the analysis, the Gittins index thing seems to be pretty specific to bandits and therefore won't be helpful to us when we're doing more general reinforcement learning.
Okay, I got to say that's very meta.
Oh, I see what you did there. Because I'm talking about thinking about different research topics as if they were bandit arms and trying to argue about, well, this one has been tried an awful lot. And so the payoff seems high, but once you know that it's been tried over and over and over again, the expected value is actually quite low. And so I'm just trying to help you, give you experience so you don't have to pull this arm.
Yeah, very, very meta.
That's cute. I wasn't thinking that way.
I'm about helping others.
All right, so we can think about maximizing reward or expected reward or expected discounted reward, but only over a finite horizon instead of this kind of infinite horizon like we talked about in number 2. And that's similar. It's something that is actually computable, but can be very expensive to compute.
Sure. So how would you actually compute that?
That's a fair question. Let's save that one because some of these problems are actually going to end up being reducible to each other. So we won't have to solve all of them independently. We just have to relate them to ones that are already solved.
Okay. Well, I will point out, since I'm being meta, that if the finite horizon is 1, then we know the answer.
Right. So if the finite horizon is 1, then just choose the one that has the maximum likelihood estimate. That's fair. And you sort of kind of generalize that idea to do 2, a horizon of 2, a horizon of 3, a horizon of 4. You can just kind of iterate it out. It's a little bit like value iteration. Right, so now we're going to have a slightly twistier kind of definition. So what about a metric like this? We're going to try to identify a near optimal arm. And near optimal means, well, we can be wrong by choosing an arm that's epsilon close to the real arm. Somebody's going to give us an epsilon as a parameter. So we don't have to get the absolute best arm because that's actually impossible to do in finite time because we could always be really unlucky and get just a strange sample where the highest payoff arm just happens to not have paid off for us. So we're going to soften it to a near optimal arm, epsilon close to the actual optimal arm. And this doesn't even have to work all the time. It just has to work with high probability 1 minus delta. And the number of pulls before we can identify or before we have identified the near optimal arm needs to be polynomial in the number of arms, 1 over delta, 1 over epsilon. There's some polynomial, we'll call it T of k, epsilon, and delta that bounds the number of pulls before we can identify the near optimal arm with high probability.
So that T is not the transition function. So you're not moving from state K to state delta through action epsilon.
Oh, good point. Yeah, that was probably not the best use of T. T here is supposed to be time. Would you like tau better?
Sure, let's call it tau. I like tau. Cool, I like the tau. All right, so I like 4 because it looks like pack learning and it looks like the kind of thing that machine learning people come up with.
Yes, it is a lot like pack learning. It's a very packish sort of thing. I had forgotten that we knew about that, but that was in our other class, right?
Yes.
Probably approximately correct.
Yeah, probably approximately bandity.
So there was one paper that actually called this PAB. Probably approximately optimal, but that didn't end up sticking. They call this PAC even though it's not really a correctness thing. It's not a classification. But the rest of the flavor of it is very much like PAC, so we just stick with that.
Well, it's a classification if the goal is to classify the best arm.
Yeah, that's a good way to think about it. Sure. So here's a metric that's kind of like number 4, in that we're gonna have some function of epsilon, delta, and k. That is going to give us a number of time steps. And in this particular case, instead of saying, well, at the end of that, we're going to know what the near optimal arm is, instead, we're going to say we're going to have nearly maximized reward over that interval. Basically, you give me an epsilon, a delta, and a k, the number of arms, and I will make a strategy and a polynomial, tau prime, k, epsilon, delta, such that if I run that long, I will get at least this close, I guess, per step to the maximum reward with high probability.
Okay. So that's like the difference between 1 and 2, where instead of the goal being to figure out what the best arm is, the goal is to pick up as much reward as possible on the way to figuring that out.
Yeah, that's a good way to think about it.
So we're actually willing to take longer to find the optimal answer so long as we pick up more reward along the way.
Could be. Yeah, it could be that there's a trade-off there. It could be that these things are relatable to each other.
At least a little bit relatable to one another, because certainly if I can do 5 quickly, I will probably do 4.
Well, we'll work that through, but I wanted to put these up as separate things, and then it turns out we can, in fact, relate them to each other.
Cool. So, but if I had to choose between one of them, I think I prefer 5 to 4 just because it does matter how I get there, not just that I got there.
Yeah, it certainly. This is going to deal more directly with reward. Look, it seems like if for number 4 we could actually potentially do a lot of really terrible stuff for tau, k, epsilon, delta steps. As long as at the end of it we go, and here's the right answer. We could sort of pop up with our hand saying, this is what I should have been doing but haven't been doing. Whereas in number 5, the money is where your arms are. That's not right, but that we're actually getting nearly optimal payoff.
Okay, that makes sense. Cool. So I can't wait to see how you relate all these things together.
There are other possible metrics. There's a very long list of possible metrics, but I just wanted to throw down one more, which is, let's say that we want to pull a non-near optimal arm, epsilon, no more than tau double prime k epsilon delta times with high probability, 1 minus delta. So basically the number of times that you pull an arm that's not nearly optimal is small. And there's over no particular time window. It could be over a very, very long time window, but the number of pulls, the number of mistaken pulls is really small.
Okay, well, that makes sense. So basically I want to minimize my mistakes, kind of.
Yes, that's a good way to think about it. Or at least bound. This is mistake bound. This is number of reward, and this is identifying near optimal. And it turns out that all of these guys are actually equivalent in the sense that an algorithm for one gives us an algorithm for the other two.
Oh, well, that's good.
All right, let me tell you about that then. So what I'd like to do is kind of talk you through the process by which we can show that these different metrics, at least these 3 metrics that I was claiming are equivalent, can be reduced to each other. That if we have a solution to one, we can use it to solve the others. So the first step of this that I want to show is that if we have an algorithm that can find the best arm, or let's say the epsilon best arm, with high probability in some bounded number of pulls, then we could use that to build an algorithm that will have low mistakes. And by low mistakes, I mean the number of trials at which it pulls a non-epsilon prime closed arm is small, is bounded.
Okay, so by low mistakes, you mean few mistakes.
Low mistakes, I mean few mistakes. I can change it to few mistakes.
Yeah, it's your choice.
That's just one of my many mistakes. So we want to construct an algorithm that if we give it epsilon prime and delta prime, that it can choose a tau prime, k, epsilon prime, delta prime, that is going to choose an epsilon prime close arm on all pulls except for this bounded number, this tau prime number, with high probability. And all we've got to work with is this first algorithm that finds the epsilon best arm in tau, k, epsilon, delta pulls. So what we have to do is define, well, if we have that algorithm, what epsilon do we give it? What delta do we give it? And how do we use it so that we have this guarantee?
Wait, why can't you just use the original algorithm to find the epsilon best one, and then you now can do an epsilon close arm?
All right, so we're going to set epsilon to epsilon prime, delta to delta prime. Then we're going to run algorithm A, and what do we do? So after tau, k, epsilon, delta pulls, we know an epsilon or epsilon prime nearly optimal arm, and we just pull it then forever, right?
Yeah.
And how many mistakes do we make?
From which point? Once we've chosen the epsilon prime arm?
Well, no, in the whole run, right? Because the idea is that we have to bound the total number of mistakes that are made. So the total number of mistakes, this tau prime, is equal to what?
Well, whatever number of mistakes algorithm A would have made in finding it.
Well, we have a bound for the number of steps before we have identified, or before this algorithm has identified a near optimal arm.
Oh, I guess it's in fact tau, yeah.
Yeah. So we just run the original algorithm until it finds the best arm, and we pull it thereafter. The maximum number of mistakes it will make is exactly the number of steps that it took to identify that arm. It may be that on some of those trials it actually was taking the best arm, but this is just a nice upper bound.
Do I have to worry about the mistakes I'm going to make at that point on?
No, because we're not going to make any more, because with high probability we found an epsilon close arm. So with high probability we'll never make another mistake. Now there's some probability that it fails, but that probability will match across these two problems, so it's okay.
Right. So the mistake is having pulled a non-epsilon prime close arm.
Yes.
Not some other notion of mistake.
Exactly so. Right. So we'll say that a mistake means that we pulled an arm that wasn't very close to optimal.
Right.
And so we just want to bound the total number of mistakes that we make.
Okay. Well, yes, that was pretty straightforward.
Good. That was an easy one. All right. So the next thing we want to show is that if we have an algorithm that has a bounded number of mistakes in the sense that we just talked about, that algorithm will eventually do well in the sense that it will achieve a total reward that is arbitrarily close, epsilon prime close, to the per step optimal reward. So let's imagine that we have an algorithm that pulls epsilon suboptimal arms at most this bounded number of times with high probability. So this is something that has very few mistakes. Oh, and except it wants to be tau. Right. Given that algorithm, we want to make a new algorithm that with high probability, 1 minus delta prime, has a per step reward that is epsilon prime close to the optimal per step reward. In other words, what we would have gotten by pulling the optimal arm on every step. And that bound starts to hold after some number of steps, tau prime, k, epsilon prime, delta prime.
So does that mean we get to do the same thing we did before?
Let's try that.
Okay.
We run this mistake bound algorithm that makes very few mistakes. So what's our tau prime? When is it that we're going to have achieved near optimality?
Because algorithm B is the same as algorithm A, it means that by running algorithm B, we're going to end up with an arm that is epsilon optimal.
Yes, that's true, but I don't want to think about it that way. I don't want to bring algorithm A into this at the moment. Let's just stick with the algorithm on the slide, algorithm B.
So we have an algorithm that pulls epsilon suboptimal arms at most that many times. That implies, the way it's written, that you could have pulled a bunch of epsilon optimal arms many, many times during that.
Yes.
But not during that time period. Like you could have pulled epsilon optimal a bazillion times and then pulled epsilon suboptimal tau times.
Yes.
And then it would be tau plus a bazillion.
Yes.
Would be the total number of steps.
Yes. So yeah, this is all true. So okay, so we need to kind of think about how we can use that fact to build a bound. So ultimately we're going to run, this is going to be algorithm C, by the way. We're going to run this algorithm C for some number of steps. We're going to call tau prime, k, epsilon prime, delta prime. And let's say that the algorithm that we actually run for this amount of time is algorithm B.
Mm-hmm.
What do we know? We know that it could be that it made tau, k, let's say epsilon prime, delta prime mistakes. And then all the rest have to be actual near optimal. In fact, it's going to be epsilon optimal. So we might need a different epsilon than epsilon prime. But so let's say that it's epsilon optimal for the rest of these steps.
Mm-hmm.
What do we have to do to make it so that this average is close to optimal?
Well, from that point on, we just pull anything that's epsilon optimal, and it'll sort of all average out, right?
No, because we don't know how to pull things that are epsilon optimal from that point on. All we know is that this algorithm B is going to make it most tau, k, epsilon, delta prime mistakes.
Mm-hmm.
So on those trials, how close to optimal is it on the trials where it actually makes a mistake?
Where it makes a mistake?
Yeah.
Something greater than epsilon.
Sure. What's the largest it can be?
1.
Good. Right. Because remember, we're talking about a Bernoulli bandit, which is a bandit you pull the arm and it either pays off with probability 0 or 1 or something in between. So the worst we can do is we pulled an arm, but it actually has a payoff of 0, but the right arm had a payoff of 1.
Right.
So the maximum error, the maximum per step reward cost that we could have in this case is going to be 1.
Times tau.
For those trials.
Right.
That times tau, that's right. So in fact, let's write that. And how close to optimal are we going to be in these other trials?
Epsilon optimal.
We're going to epsilon, right? All right. So this is going to be our total suboptimality over the n steps.
Mm-hmm.
And our average per step optimality is going to be that.
Right.
And we want this to be bounded by epsilon prime.
Yes.
And we get to pick two things, right? We get to pick n and we get to pick epsilon. So can we solve this? How do we do that? So I'm going to suggest that we just pick an epsilon. It's going to be problematic if we pick epsilon to be epsilon prime, because then we're making these big mistakes here and we're making even bigger mistakes there. So on average, it's not going to work out.
Mm-hmm.
But if we set epsilon to epsilon prime over 2, right? So we want our average per step reward to be epsilon close. But to do that, we're going to run this algorithm B with an even tighter epsilon.
Okay.
All right. So that gives us this inequality with only one free variable, which is n. So how big does n have to be so that everything works out? So that should be solvable.
Yeah, you multiply both sides by n, you do some algebra.
Okay, so the algebra got us to this point where we say that the n, the number of steps that we need to run before we have near optimal reward per step, is at least m, the number of mistakes that the algorithm B is going to make, times 2 over epsilon prime minus 1. So epsilon prime, if you think of epsilon prime as being some teeny tiny number, so 2 over epsilon prime is going to be some fairly big number. We have to run that minus 1, but it's still polynomial. in the epsilon prime that we were originally given.
Right, or 1 over epsilon prime. So epsilon prime has to be
less than 1.
Right.
So we're good. I mean, what's going to happen here is we could get something like 2 over 1 minus 1, which is going to be 1. But as epsilon prime gets closer and closer to 0, this blows up. But again, it's polynomial in 1 over epsilon prime. So we're good. It just means that we have to run a bit longer than the number of mistakes that we are bounded by, so that on average things work out, because we're going to be essentially optimal here. We're going to be epsilon over 2 optimal here. And so when we actually work that all the way through, we're going to get something that averaged out over this very long time interval. It's nearly optimal per time step. So that the reward that we're going to get is actually close to optimal. So I'm going to claim this is the last relationship that we have to build to prove that they're all equivalent. But we'll pull that all together at the end. But this is going to be the hardest one. So this one says that if we have an algorithm that does well on average per step, right, it's nearly optimal per step, then we can use that to build an algorithm that actually identifies an arm that is nearly optimal. And so this is what we're imagining. We imagine we have an algorithm, and we were calling it C, I think, that gets within epsilon per step of optimal after some number of pulls with high probability. So after this tau, k, epsilon, delta pulls, then the average reward that we've gotten is close to the average reward that you get if you were pulling the optimal arm on every step. And what we want is algorithm A, which after some number of pulls returns an arm that is epsilon prime optimal. So someone has to tell us k, the number of arms, epsilon prime and delta prime. Oh, and this holds with probability 1 minus delta prime. Then what we get to do is set up this other algorithm C however we want, and run it for how long it runs. And at the end of that, somehow use the information that was gathered to pick an arm that is nearly the best.
Right, and I just realized something that I think was obvious, but I actually wasn't thinking much about, so I should say it out loud, which is we're going to take the epsilon prime and the delta prime, and we're going to create some epsilons and deltas. That has to be polynomial.
Yeah, because if we did like 2 to the 1 over epsilon prime or something like that, then we've actually made things really bad.
Right. So it has to be polynomial. Okay, that's worth remembering.
And that was true in the other 2 examples that we did, and it's going to be true in this one too.
Right, sure. It just occurred to me that you could cheat if you could just do any arbitrary epsilon to epsilon prime.
Yes, just set epsilon to 0, and yeah.
Yeah. Okay, cool. All right, so I think I have half an answer here. So maybe half the answer will help towards the full answer. So here's the half the answer. If I've run algorithm C and I've got a per step near optimal payoff, then one thing I know is that if I were to keep following whatever distribution of pulls, of sort of banded arm pulls that I'd done before, I would still have the same per step average.
So here's what we're going to do. We're going to introduce an additional epsilon looking thing. We'll call it E sub I, and that is the suboptimality, or the error, of the plurality arm chosen by algorithm C, right? So there's going to be some arm that gets chosen more than the other arms, or as much as the other arm, but no less than any of the other arms. And we'll call that arm I, and EI is the suboptimality of that arm. So what do we know? We know that this arm is chosen at least 1 over k of the time. So the total per step error, epsilon, has to be at least as big as EI times 1 over k.
Right.
Yeah, right. Okay, so if we rewrite this in terms of a constraint on EI has to be less than or equal to epsilon times k. But we want to set epsilon so that the suboptimality of the plurality arm is less than or equal to epsilon prime, right? So that's the constraint that we're given. We need to figure out a way of running things so that the plurality arm is epsilon prime optimal. So we want this plurality arm to be less than or equal to epsilon prime. So if we set epsilon equal to epsilon prime over k, then everything holds, right? So over here, epsilon over k greater than or equal to this implies that epsilon is greater than or equal to E sub I, which is exactly what we wanted. So this implies the right thing.
Right, and in fact, you could get the epsilon equal to epsilon prime over k just by doing algebra, right? You got e sub I less than or equal to epsilon prime, and we know that e sub I is also less than epsilon times k, so we want epsilon times k to be less than or equal to epsilon prime. Therefore, epsilon is equal to epsilon prime divided by k.
Good. So if we set that epsilon, and then we run algorithm C for tau steps, then the arm that we get at the end of that run that's chosen most often has to be nearly optimal, right? Because if it wasn't nearly optimal, then we would have actually accrued a lot more per step error. So that actually does it. We actually can. It just the fact that we can do arbitrarily well means we can find something arbitrarily close to the best arm.
Wow. So that's brilliant. So whoever came up with that proof is one smart, handsome guy.
So now that we've gone through that exercise, let's put these pieces together. We showed 3 separate results: that being able to find the best or nearly the best lets you make few mistakes. Being able to make few mistakes lets you do well on average per step. Being able to do well on average per step gives you the ability to actually find a nearly best arm. So all these things are actually equivalent. If you give me an algorithm for doing any one of these, I can derive something for doing the other 2. Just kind of do it in a circle here. So in a sense, what this is telling us is that we kind of don't have to pick among these 3 different optimality criteria because they're really all the same as each other. And you could sort of say, well, and must be that these are the right ones to think about, because even if we don't think about, say, this doing well on average per step, we would have to solve it anyway if we cared about any of these other things. So I don't know. I mean, what I get out of this is the idea that whichever of these is most convenient for you to work with, you should just work with it, because the other ones are going to fall out. And there's other optimality criteria that you could worry about, but I don't know. It seems like a lot of them come back down to these.
Yeah, I like that a lot. You're really saying that they're kind of in an equivalence class of difficulty.
Yes. Now, interestingly, the thing that we haven't done yet and that we need to do is show that we can solve any of these problems.
I thought we just did. We did put a lot of words on some screens, and there were some taus.
No. No, what we showed was that if you could solve one, you could solve the other. If you could solve that one, you could solve. But we never said that any of these are actually solvable. And so we need one more result to kind of make this all doable.
Okay, that's fair. But so I don't know. I was satisfied with proof by tau. But if you want to, actually go and ground it out.
Yeah, but all the taus were defined in terms of other taus. It never bottomed out. Right? What we'd really like is something that says, here's an algorithm that will, in a polynomial number of trials, find you a nearly optimal arm.
I don't know, Michael. It seems to me this is pretty straightforward. It's taus all the way down.
It can't be taus all the way down.
Why not? It's turtles. They start with the same sound.
That's true. I guess they're Greek turtles.
Yes, it's Greek turtles all the way down, which is what we've always suspected.
So at the bottom of this stack of turtles is a turtle named Hufting. And Hufting gives us a solution to all the rest of the turtles. There's actually a bunch of different names for this. I've heard Chernoff. I've heard other things. Tail bounds, which you can see the tail is bounded because I forgot to draw it. That all kind of boil down to the same thing. So I apologize to any person who may have derived one of these bounds who I didn't show proper appreciation to. But this is the general flavor of it.
Well, I think the most important thing is that you find someone who did the derivation who's Greek, since all the turtles are Greek.
Except for Hufting, as it turns out. So here's the form of the Hufting bound. So the Hufting bound says that if we have a set of n random variables, x1 through xn, and let's say that they're all IID, which is independent and identically distributed, and each one has a mean of mu, and let's say that we observe these values. So it's a bunch of 0, 1s. Mu hat could be a good estimate of mu, right? It's like add up all the variables that you saw, all the 0s and 1s, and divide by the number of them that you saw.
In other words, the maximum likelihood mean.
Yes, which is exactly the maximum likelihood estimate. So it's a maximum likelihood estimate, but the bigger n gets, the more confident we get as to how close we are to it. So this is what gives us a way of quantifying this. So the following is a 100 times 1 minus delta % confidence interval for mu, right? So we don't know mu, but we know mu hat because we can get it just by averaging these values together. We're going to say that the real mu is highly likely to be between mu hat minus z delta over root n and mu hat plus z delta over root n, where z delta is the square root of 1/2 times log of 2 over delta.
Oh, right. That's obvious.
Well, it's maybe not obvious, but it does have the right kinds of properties. So in particular, I don't think I can justify this too without going through the detailed derivation of the bound. But why is the delta where it is? Well, the more confident that we want to be, the smaller delta gets. And that means that this quantity gets bigger. The log of that is still very big. The square root of that is still very big. So this z delta is very big. And so the width of this bound ends up being very big. If we want to be really, really sure, we need to give a big window so that we're really sure that we're in that window. But on the other hand, if we have a lot of data, if we have a big n here, that tends to make the bounds smaller. They shrink with the square root of n. So if we have, like a billion for n, then it's going to be mu plus or minus some quantity divided by something really big. So it's going to be just a small little interval around our estimate. So it has the right kind of properties, but the fact that it's a square root of a log and there's a 2 and then a 1/2 and stuff, that's maybe not so obvious.
Well, it looks a lot like, in fact, we used Hufting bounds when we were doing pack learning.
Yes. And again, these learning results that we were just talking about have a very pack kind of feel to them. So it's maybe not so surprising that the bottom of the stack of turtles is a turtle named Hufting.
That's cool. So basically everything really does all tie together.
Yes, at least as long as you think about things this way. So, okay, but this isn't quite answering our question, but this is going to be the key tool for answering our question. So given that we have a way of knowing how close we are to estimating a hidden parameter from a sample, we can then use that to figure out how many times do we have to pull an arm before we know fairly accurately what its payoff is. And therefore, if we have k arms, how many times we have to pull each of those arms so that we're very confident that we find something nearly optimal amongst them.
Beautiful. I don't yet know how this is going to solve everything, but I can see how it's a step in the right direction.
So the information about the Hufting bound gives us a way of thinking about how many samples we need to accurately learn the value of an arm. So we're going to have to actually pick a number for that, how many samples we're going to take of each arm. To guide us in that decision, it's going to be helpful to think about how we're going to combine information across the arm. So this is going to be a strategy that will ultimately work, though we don't have all the details filled in yet. And it goes like this. What we're going to do is we're going to take C samples of each arm for some value C.
Yeah, that's what I was going to do.
The C is going to be some function of epsilon, delta, k, that sort of thing. But it's going to be some number, and it's going to be a number that, we're going to see. So it's going to be some number that guarantees that we're some amount close with some certainty. And then after that point, we're going to choose the arm that has the highest estimate, the best estimate.
All right.
Ultimately, we want our final decision here to be epsilon close to the optimal decision with probability 1 minus delta. So I claim that to do that, for this to work, we need to learn each arm individually to an accuracy of epsilon over 2 and with a certainty of 1 minus delta over k. All right, so instead of doing a super duper formal proof, here's how I like to think about this particular result. So here's a picture that I'm hoping is helpful. It's kind of a weird graph of the x-axis is the arms. In this case, this is a 5-arm bandit. And the y-axis is the value of that arm. And these rectangles represent our uncertainty intervals of that arm's value. Does that make sense?
They're not the arms themselves. That's just the uncertainty.
Yeah, if they were actually arms, then I'd have to draw like. Oh, that's terrible. That was supposed to be a hand. So I apologize.
That's a 7-fingered hand. That's okay.
Yeah, I think that was the problem. Because you know what it is? It's to make up for the fact that like Mickey Mouse only has 4.
That's perfectly reasonable.
So if we do this, if we make sure that each arm, we are 1 minus delta over k sure that its estimate is within epsilon over 2 of what our sampled evaluation is. So how big are these bars exactly?
Oh, okay, I see. So those are uncertainty bars or error bars. So that means your estimate is right smack in the middle of each of them.
Right. So we have our estimates for each of the individual arms, and that estimate is, we're pretty sure, epsilon over 2 close to the actual value.
Right. So that would mean that you could be epsilon over 2 too high or epsilon over 2 too low, which means the total height of those bars is 2 times epsilon over 2, or epsilon.
And those estimates hold true with some probability.
Sure.
So each one is correct with probability 1 minus delta over k. So the first thing we need to do is basically make sure that all these estimates are correct. Because if one of them is wrong, then it casts doubt over the entire calculation. So what's the probability that all of these estimates are actually correct simultaneously?
Well, If I pretend they're all independent of one another, then isn't it just 1 minus delta over k to the k?
Delta over k is the probability that a given arm is wrong. 1 minus delta over k is the probability that that arm is right. So if that probability is 1, for example, then, raise that to the k power. Sure, they're all going to be right because they all have certainty of being right. But if it's a little bit less, 0.95 or something like that, then it's 0.95, and this one has to be right. That's another probability 0.95, and this one has to be right. So we end up with the raise to the k power of that individual arm probability.
Right.
It turns out for various reasons that this kind of quantity is hard to work with, and also sometimes, I think not in this case, but sometimes it's also a little risky because it assumes statistical independence of all the estimates, and sometimes it's safer to just say, maybe they're not independent of each other. Maybe they actually all fail together or all fail separately. So we use a standard trick to get around this idea. And this is the idea that we can estimate the probability that at least one is wrong. If we know the probability that one is wrong, it can't be, since there's k of them, it can't be any worse than k times delta over k. And this kind of follows from, if you think of it as like a Venn diagram, there's, here's the probability that one thing is bad. Here's the probability that the other thing is bad. Here's the probability that the third thing is bad. What's the largest that this can be? The maximum badness probability is actually going to be the sum of these if their intersections are all 0. And so this is really like taking the union of all those sets. So this is referred to as the union bound, which, I don't know, to me sounds like kind of a fancy name for not such a fancy idea. We're just going to add the probabilities because we don't know how to account for the overlaps.
Oh, but that just follows from probability, right? The probability of A or B is just the probability of A plus the probability of B minus the probability of A and B. And sort of the worst case in this situation is that A and B is 0.
Right. So this is just how these probabilistic quantities are defined. And what we're saying is if we want to maximize the probability of this or, that at least one of them is wrong, then if we set this intersection as 0, that maximizes it. So it really is just the sum is an upper bound. So what the union bound gives us then is this idea that if each of the arms individually has a certainty of 1 minus delta over k, then all k of them together have a certainty of at least 1 minus delta. So that was what we wanted. And now the last thing that we want is to know that the arm that we pick is within epsilon of optimal. So what gives us that? Well, I mean, the idea is that whatever truly optimal is in this case, it might be at the bottom of a bar's range, for example.
Whatever's optimal cannot be at the bottom of a bar's range.
Ah, yes, good point. But it could be at the top of the wrong bar.
Right.
Not the bar that we think is the highest. So here we think that this bar here, this third bar, is the highest. But its true value might actually be all the way down at its bottom. Whereas some other bar that looks lower than it, its true value might be actually much closer to the top. So the worst case is what happens is we have one bar that's infinitesimally above another bar. We just pick it because it's slightly better. But in fact, its actual value is down at the bottom. Whereas we failed to pick this other arm that has the optimal in it, and that optimal is at the top of its range. So the most we can be off, we pick this arm, the most that arm can be off is the height of the bar, which is epsilon.
Right. So that makes sense, although I don't think it has to be infinitesimally lower.
Oh, you're saying if it's just a dead tie and we picked arbitrarily.
Because you got to pick one of them.
That's true, and we could pick the wrong one.
Right, and the wrong one could have been as far off as possible, and the one that we didn't pick could have been as far off as possible in the right direction.
Cool, okay.
And then you'd be epsilon away, as opposed to epsilon minus epsilon.
Epsilon minus epsilon, which I feel like is small. Okay, all right, excellent. So that gives us both pieces here. That means if we can just figure out how many times to sample an arm, so that the guarantee that we have is that the value that we predict is within epsilon over 2 with confidence 1 minus delta over k. Then putting all those estimates together is going to get us an arm that is epsilon optimal with probability 1 minus delta.
That's perfect. And we know how many to sample.
We do. We're just going to do a little bit of algebra and we're there.
Okay, cool.
All right, so now we're going to figure out how many samples we need. And in particular, we want to be epsilon over 2 accurate in our estimate. And we want to be 1 minus delta over k certain that our estimate is correct. And so just substituting those values into the Hufting bound that we had before gives us 1/2 times natural log of 2k over delta, the certainty parameter, divided by square root of c, the number of times we do the sample, is going to be less than or equal to epsilon over 2. So now we just have to solve for c.
Okay, that seems pretty straightforward.
All right, so substituting these constraints, the epsilon over 2 and the 1 minus delta over k, into our Hufting bound from before gives us something that looks like this. Square root of 1/2, natural log of 2k over delta in the numerator, square root of the number of samples, c, in the denominator, and that gives us an estimate that's within epsilon over 2. So now we should be good to go. All we need to know is how big does c have to be? So we just have to solve for c.
Right. So we do some algebra and some other algebra, and the right thing happens.
All right, so I did the algebra, except I kind of left out some stuff. I left 2 holes in here that I want you to fill in.
Because you hate me.
Well, I just want to make sure that you're kind of, following along.
All right, fair enough. I can do that. It should be straightforward because algebra.
So, Mr. Algebra, what do you get?
That's Dr. Algebra. I did not spend 12 years in evil algebra school to be called Mr. Algebra. Okay.
My apologies.
All right, well, I think there's actually only one answer here, and that answer is 2.
All right, which one is that?
Both of them.
So there's 2 2's?
2 2's.
How do you get that? Okay, so you squared both sides, and that causes the epsilon to be squared. It gets rid of all the square roots. Then, but then we get it, because we squared both sides, we get it divided by 4 over here, which ultimately is going to meet up with the half over here, and we're going to get a 2. Yeah, that's right. Very good.
And thus more proof that every single thing in computer science gets generalized once you have 2 of them.
2 is important in computer science. So let's see what we actually get here. What we're saying is that if we sample an arm at least this many times, 2 times 1 over epsilon squared. Now, 1 over epsilon squared is polynomial in 1 over epsilon, 1 over delta, and k, times the logarithm of 2k over delta. So again, this quantity here is polynomial in k and 1 over delta, and we're logging it. And that gives us a count that if we do that enough times, we're actually going to be sufficiently certain that we're sufficiently close that choosing the maximum arm is going to be a good idea. And it's interesting to note here that the dependence on the certainty parameter is actually quite weak, right? So it's 1 over delta, and it's stuffed into the log. So this is having not a huge impact. But the dependence on the epsilon parameter is actually quite profound. It's 1 over epsilon. So if we're talking about like 0.00001, that's like, I don't know, 1,000 or 10,000 or something. And then we square that. And so we could actually need a ton of samples if we want to be very, very sure that we're very, very close. In fact, even if we want to be moderately sure that we're very, very close, there's just this big dependence on the epsilon.
So what you're saying is that the hard part is getting very, very close, not being certain how close you are.
It looks that way. Yeah, that's what this equation is telling us.
So we've said this before, since it's all hufting here and hufting there and hufting all the way down, that you're going to get stuff that looks like pack bounds. But this looks really similar to the pack bound for agnostic learning, right? There's like a 1 over epsilon squared and a natural log of delta in there, 1 over delta or something in there.
Yeah, and it uses a union bound too. It uses the union bound and the hufting bound, just like we just did. But I mean, it's not exactly the same thing, but you're right. It has a very similar flavor.
I look at this and I just think one of these looks a lot like this says something about hypothesis space, and the other is about the error. And it just feels like there's a connection there.
That there's a sense in which you can think about the payoffs of the arms as hypotheses in some sense. Or each arm is a hypothesis, and we want to find the best hypothesis. It's like finding the best arm. It has the lowest error or the lowest suboptimality. Yeah, maybe. Other than using one kind of math to solve the other kind of problem, I don't quite see what leverage we get from that. But that's a good observation.
Well, in that case, K is the hypothesis, is the size of the hypothesis space.
Yes, like the number of arms, exactly.
Right. This just seems like there's something there. I don't know. I'm sure that if we thought about it long enough or gave someone a homework problem, they'd be able to connect the two.
So just to sum up here, what we've been figuring out is a kind of pack-style bound for these kinds of bandit problems, that we want to say we can get near-optimal payoff after a polynomial number of pulls, or we can get a near-optimal arm after a polynomial number of pulls, or we can make only a polynomial number of mistakes in an infinite run, that all these things actually all boil down to essentially this result. We just have to pull each arm enough times that we have an accurate estimate.
That's pretty good. Well, pack style is better than either monkey style or crane style.
Your monkey style is quite good.
I'm impressed with your pack style.
So I promised that we would do stochastic banded arms, deterministic MDPs, and then ultimately combine ideas together and handle general stochastic MDPs. So I think we can do efficient exploration of deterministic MDPs relatively simply, actually. Here's a little randomly generated MDP, randomly generated in that I drew a bunch of arrows, and I have absolutely no idea what the solution to this is. But if we were doing reinforcement learning in this MDP, all we would know at any moment in time is which state we were in and which action we were choosing. And so an action in this case would just have a label like action 1 and action 2. I made 2 actions for each of these states. You know, we know how to solve a deterministic MDP to figure out the optimal policy for it, but we can't solve it in the beginning because we don't actually know any of this stuff, right? All these numbers, where do the arrows go and what reward do we get on an arrow? We don't know any of that at the beginning.
Right. So 2 observations. One, you don't have 2 actions at every state.
Oh, what do you mean?
Well, the one that has a 3 coming out of it, there's only 1 action that comes out. You don't have a self-action.
This one.
Yes.
Dope. All right. There's just 2 things. They both have a +3. But you're right. I thought I got them all, but I missed that one.
Doesn't really matter. So that's one observation. One observation is 1 does not always equal to 2. The second observation is that if we know it's deterministic, then all we have to do is in every state try every action once.
Yeah, that's true.
And then we know everything we know about which action is best or whatever. Magic. Something like that. Shouldn't that work?
Okay, well, you're kind of onto something. It's certainly the case that once we've tried each action in each state, then we can actually build the entire MDP and solve it.
Right.
The question is, what do we do along the way? What do we do when we don't have the whole MDP yet? Maybe it's not entirely clear. I mean, if we could just teleport ourselves to any state that we wanted to be in and take the action at that state, then that would be fine. But that's not how the world is in reinforcement learning, right? We actually are, all we can do is choose actions. We can't choose which state to be in.
Well, we could track every state that we've ever been in and every action we've ever taken.
That's true.
And then just, do things that seem reasonable, explore a little bit randomly so that we make certain we get to every state and get a chance to take every action and then kind of go.
All right, so you're thinking explore randomly so that we hit everything. That could work, but we can make MDPs where that's problematic because if we choose actions randomly, we keep, for example, getting reset to some beginning state, and actually not choosing things randomly so that we visit all the states can be challenging.
So that's true, Michael, but if we don't know anything about the MDP, then I can always construct, an MDP that's going to mess with whatever exploration strategy you have, right? Because there'll be some state with some action that puts you into some state you can never get out of. So unless you can do random restarts or, be able to get to some state, press a button and do a reboot, you could always get unlucky and never be able to explore the MDP.
Okay. All right. Well, that is a fair point. We have to be very careful about what we think our criterion is. Now, we went through it pretty carefully in the case of bandits, but I kind of jumped to deterministic MDPs without revisiting this question. So I'm gonna propose a particular optimization criterion, and then we'll talk about why it needs to be like that.
Okay, that seems fair.
We're going to talk about some possible MDP optimization criteria, and I guess this isn't really an optimization criterion, but we talked about exploring randomly being problematic because you can have MDPs that look like this, where there's a chain and you have to keep taking some specific action to get to the high reward state. And if you're always choosing actions randomly, then the probability you even ever reach that is exponentially small. So we have to be a little bit careful. For example, in this MDP, it's not really clear what to do from this state.
From which state? That state? No, it's pretty clear what to do from that state. Go left.
Oh, okay, sure. No, I mean, in the reinforcement learning setting, we have just 2 actions. If we choose wisely, as you just did, then we end up in this state and we get reward, and that's yay. If we choose not wisely, then we get stuck in this trap state and we get bad reward forever and there's no way out. And so in the reinforcement learning setting, we don't know where the different arrows are pointing until we try it. So it's a little bit unfair to say what we should be doing is maximizing all possible reward values, right? Because it could be that we get ourselves into a position where we just can't anymore. So here's what I advocate. Remember we talked in the bandit case about a mistake bound, the idea of the number of times you pull an arm that's not the right arm to pull is bounded by some polynomial. It turns out that works out really nicely in MDPs as well. So the idea is that, think about this state here in this trap example. It has only one action choice from this state. So what's the right action to choose from here?
The one action?
Yeah. So we're not wrong.
True.
Right? And so in fact, no matter what in this particular MDP, the total number of mistakes we could ever make is 1, right? We might make this wrong first action, and then we're making optimal actions thereafter. I mean, again, optimal is relative to the state that we're in, but we're in the state that we're in.
Oh, that's kind of deep. Okay.
Thanks. So the criterion that I'm going to advocate for here is that what we're going to do is count the number of epsilon suboptimal actions. That is to say, the number of times that we're in a state, we choose an action, and that action in that state was not epsilon close to the best action in that state, that we want that to be bounded by some polynomial in, let's say, 1 over epsilon, 1 over delta, the number of states n, and the number of actions in each state k.
Okay. Okay. So the actions are like bandits. I like where this is going.
A little bit. We're going to bring it all together. So this wasn't really an analysis of different criteria. This was basically me just trying to justify one criterion because it has some nice properties. It lets you deal with the fact that there can be trap states, and that doesn't hurt us in the learning setting. And, well, we're going to have to come up with an algorithm that's going to deal with this randomness case, this you can't explore randomly idea.
Okay. So I think there should be a fourth criterion, by the way, which was inspired by your recommending that I listen to William Shatner sing, which is the Kobayashi-Maru criterion, which is we minimize the number of times we have to cheat.
I do not remember recommending that you listen to William Shatner.
But everyone should.
Okay, but that's a separate issue. So minimize in the Kobayashi-Maru test, he reprogrammed it so that he could win, even though you couldn't win. So this is kind of like that, in that we're defining winning. That's not really like that, but it's defining winning to be doing the best thing given the state that you're in, and it's not actually penalizing you for having done something really stupid for having gotten into that state, as long as the total number of really stupid things is bounded.
Everything really does come back to Star Trek. Okay, I buy that. 3 and 4 are the same.
Well, we can't cheat. You can't cheat in reinforcement learning.
Oh, I beg to differ.
Again, what we're trying to do now is explore a deterministic MDP and have low mistake bound. The number of actions that we take that are suboptimal by more than epsilon is going to be, we need to bound it in terms of things. So let's try a little experiment. You're going to be the reinforcement learner.
Okay.
And I'm going to be the environment and tell you what's going on. So let's say we start off in this state here. Which action do you want to do, 1 or 2?
I want to, do I get to cheat and look to see what the...
You could, but I think that somehow isn't going to be quite as pedagogical.
Well, we'll learn a lesson for sure. I'll do 1. I don't even know which one is 1 and which one is 2 anyway. I'll do 1.
Yeah, I get to pick that. That's the good news from my perspective. I'm sorry, that cost you 8 points.
No.
Yes, but now we're here. So do you want to do 1 or 2?
Let's do 1 again.
That's not bad. You got +2 and you didn't go anywhere.
Just like grad school. Well, I've done 1. I know what that is. So let's try 2.
Okay. +10, so that's really good, but now you're someplace new.
Can I invent a time machine? Let's do 1.
Let's do 1. -6. Ouch. Now you're here.
All right, let's do 1. You know, when I was in that other state and I got a +2, I could have just stayed there forever. In fact, that probably was the right thing to do because I get infinite reward.
Well, it's discounted.
I set my discount to be 1.
No, you don't get to choose that.
That's not fair. Okay, so I'm sorry. I interrupted you.
All right, so you chose action 1. So I'll give you 1 point for choosing action 1.
And I end up in another state. All right, well, let's do action 1 again.
All right, so +1, and you get to be there again.
You know, if I just keep doing action 1 over and over again forever, I'll accumulate infinite reward.
No, sorry. You'll get 1 over 1 minus gamma.
Okay, I'll set gamma to be equal to 1.
No, that's not one of the choices I was giving you. You can choose actions.
Ah.
I should probably have told you gamma. I guess that would only be fair, right?
Well, I guess I'm not sure it's going to matter if gamma's less than, just as long as gamma's less than 1. All right, so I now know something.
You now know something. You know a lot of things.
So I do know a lot of things. I'm still in the same state, but I've got another action. I don't know anything about it. Let's try action 2.
+6, yay! And now you're at a state you've never been to before.
This reminds me of Zork. Okay, I'll take action 1.
It is like Zork.
It's exactly like Zork.
Hey, you're back to the state that you started in the very beginning.
I know -8 sucks. Actually, I now could basically do that cycle forever.
The series of actions that you just did that take you around this loop. Yes. Is that near optimal?
Well, if it involves -8, probably not. Let's do action 2.
Good idea. All right, so you're back to another state you've been to before.
And I got a -3 along the way, which is better than the -8. But not better than the -8 plus +2 some number of times +10, except gamma 0.9. Okay, so I know what action 1 gives me there, so let's do action 2.
Good job, you got a +4. and you're back here.
Oh, I'm in a nice little state too, and I can do some little cycling.
Yep. And you tried action 1 from there.
Oh, but I never tried action 2 from here, did I? Let's do action 2.
All right, so action 2 turns out to be identical to action 1.
Oh, okay. That's complicated.
Cool. So now you're back at the initial state that you started in the beginning of time, and both actions that you have here, you've tried already.
And so I can say something about what could happen after that point, right? I know sort of if I take action 1, I get -8 plus 2 for some amount of time, plus 10, sort of the best I could do.
-10. Plus 10.
Plus
You're
10.
Right.
Or I could do -3 and get immediately to this thing where I could go get +4s and +3s, which actually is better, I think. So I should pick one of those.
Well, okay, so here's an important point that we need to get to. So actually, you've explored the entire MDP except for one state action pair, this one here. And so if this edge is like a self loop with a reward of 1,000,000, then you have to find it. You have to get it, because otherwise you're not going to be nearly optimal.
Right, and I don't know that. So I have to get there.
Right. But on the other hand, let's say that we know that the highest reward is 10.
Okay.
So we have some bound, we'll call it Rmax,
All right.
on the largest reward in any state.
Mm.
Well, that could be really helpful, right? Because it could be that I can get a value by acting in the MDP that I have now, that even if this were 10, even if it were its highest possible value with, let's say, a self loop, we can still do better than that.
This feels very minimax.
Well, it's Rmax.
No, I mean, this feels like, it's a tree and I could do pruning. I mean, what you're basically saying is I should prune things if I already know that I can't do any better than some other choice that I have.
Yeah, that's right. So it has a boundish kind of feel to it. So what I'm suggesting is for any edge that we don't know, let's just be super optimistic and assume that it has value Rmax.
Yeah, that makes a lot of sense. And then I can already, if I pretended that's true for everything that I don't know, then that would tell me what to do, sort of in what the best worst case would be. And then I should try to get to the place that I think is good because I'm optimistic. And if it turns out I'm wrong, well, as soon as I get there, I will know that I was wrong. And I just keep doing that.
All right, let's write down the steps so that we don't have to hold them in our head so long. All right, so 1, keep track of the MDP we have so far. And we're saying that any unknown state action pair is an Rmax self loop.
Okay.
Right? So we can get the maximum amount of reward, and we can get back to that state and get it again and again and again and again. So clearly there's no policy that's going to be better than that from that state.
Right.
All right. So then we're going to solve the MDP with those, again, the assumption that anything we don't know is Rmax.
So solve the MDP assuming 1 and 2.
And then we go back to 1, essentially, right?
Well, you just execute the optimal policy.
Like that.
Yeah. And then as we take those actions, we may discover that some of the 8 action pairs were wrong, but we'll just fix that by doing 1, and we'll just solve the new MDP.
Good. All right. So there's a couple things we need to convince ourselves about this. Right? One is that we get epsilon optimal reward.
Yeah.
Another one is that the number of mistakes that it makes is going to be relatively small.
I think the second one's probably pretty easy, right?
Well, let's go. All right, so let's talk through the analysis of this algorithm in deterministic MDPs. I'm going to call the algorithm Rmax because anything we don't know we assume is Rmax. It's not a great name, I guess, but it is the name that it was given by Brofman and Tenenholtz when they first proposed and analyzed it. I guess it had another name too.
Armin?
No, because the algorithm actually is directly related to an algorithm that Andrew Moore proposed, but didn't have an analysis for it.
So it could have been Armor.
I see. Rmax, and even more than that is Rmore.
Mm-hmm.
All right, let's just go with that. So here's the algorithm. I just copied it from the previous slide. And there's some things that we can figure out about this. Like, once we've actually visited all the state action pairs in a deterministic MDP, then this algorithm is going to be perfect. It's never going to make any more mistakes after that. Right? Do you see that? Because it's going to, in step 3, it solves the MDP, which is in this case now the actual optimal policy. And then any action that it takes from that policy thereafter is going to be an optimal action, not a mistake. So this is great. If it's the case that we eventually visit all of the edges in the MDP, then we'll make no more mistakes after that point.
How do you count mistakes, though? You count mistakes on a per-state basis?
Yeah, a mistake in this case means I'm in a state, I take an action, and that action wasn't near optimal from that state.
From that state, right.
All right, but we need a couple more things here, right? So it could be that we never actually know the whole MDP.
That's possible. For example, if we're in one of those trap states.
What happens if we stop visiting unknown states? right? So what would that mean? In the case of a deterministic MDP, it would mean that we're following some policy that is taking us on edges that we know about. And this is so nothing new ever happens, nothing new is ever learned. But there could be other unknown edges elsewhere in the MDP that we're not visiting. So could we be making mistakes as we go around this loop over and over and over again?
If we can get to that state from any of those states, then we would end up going to that state because we assume it's the best thing that we could do.
Not necessarily. So here's a tiny little example. So let's say we're in this state here that we know has a self-loop of +5, and the discount factor is 0.5.
Okay.
So what's the value of actually going around this self-loop over and over again?
5 times 1 over 1 minus 0.5, so 10.
Good. And let's say that our max is 10.
Okay.
And we know that the only other action that we can take from this state goes to this state, which has only one action, and it takes us to this state, and we have no idea what happens from there. So what do we assume?
Well, we assume that you can always stay there forever doing 10.
And the value of that at this state would be 20.
Right, for the same reasons.
And the value of that at this state would be 10. And the value of this action at this state would be 5. So from this state, from this bottom state here, even if this has the maximum possible reward and a self loop, the most value we could get out of that from this state is 5. It's a double discounted 10 loop. So that means that we know that the optimal action from this state is this +5. It's going to be better than even the best that could possibly be out there. So we're good. It might be lower. I mean, it could be that this unknown thing is even lower, but that only strengthens our case that we were doing the right thing. So the point is that we can actually be in a loop that uncovers no new unknown edges, right? It never visits something that we haven't seen.
Mm-hmm.
But we still are not making mistakes, and we know we're not making mistakes because if we're choosing this path over something that uses these optimistic estimates or these optimistic assumptions, then we're doing at least as well as the best we could do.
Sure, how about that? I mean, although that takes advantage of something that's always bothered me.
What's that?
You set gamma to be equal to 1/2, right?
Yeah, that was just to, we could be bigger, but I just didn't want to do the math.
No, I'm with you. So you said gamma to be equal to 1/2. And so with gamma equal to 1/2, that's true. But in reality, when we keep track of whether an algorithm is doing well or not, we don't actually discount the rewards that we see. We just add them up.
So we're not going to go down that philosophical rabbit hole. We're going to accept discount factors for now. I agree with you that discount factors are a little bit hard to swallow. If we don't, though, I don't think we can make any progress.
No, I agree. It does make sense. It just seemed like it was worth mentioning that, you have to take the discount factors seriously, that the future really is going to be discounted from any given point where you are, because otherwise it actually makes sense to get to that 10.
Yes, you're absolutely right. Like if we don't have a notion of a discount or the discount is really, really high, then it could be that the highest this could be is going to give us better than the repeated +5. So yes, we are definitely leaning hard on the notion of a discount factor.
Right. And in fact, if the discount were 1 or essentially 1, and we know that our max is actually right, whatever our max value is right, then you basically, unless you encounter the actual self loop +10 or R max, then you have to explore the entire MDP. You must. It'll just sort of force you to.
Well, okay, we'll do that as step 3 of the analysis. So let me finish this step 2 first. So what I'm claiming in step 2 here is that if we end up choosing a policy that is not based on knowing all of the transitions, like there's still some unknown transitions out there, but we end up taking a policy that puts us into a loop where we never visit any of those, then that still has to be an optimal loop. We're not making any mistakes.
Right.
It could be that we could do as well by uncovering those other values, but we can't do any better because we are assuming in step 2 that anything that we don't know has the largest possible value.
Right.
And so if it has the largest possible value and we still don't want to go there, then we're doing at least as well as optimal.
Yeah, that's kind of cute.
All right. So, but now we need step 3. So now step 3 says, okay, we solve the MDP, this sort of imagined MDP that has these optimistic estimates in it. And let's say that actually takes us to a state action pair that we haven't been to before, and we learn its value.
Mm-hmm.
How many mistakes might we make en route to that? So when we actually get to that state and traverse an edge that we didn't know about, that could have been a mistake.
Right.
So that's definitely, 1. And how many mistakes might we make, seeking out this state that actually turned out to be a really bad state?
From a particular state, I guess the number of states.
Yes. Right. So the number of transitions that we might take just to find out that we were wrong could be as big as n,
Right.
the number of states.
Or n minus 1 or something like that. But yeah.
Yeah. So en route to a this is in a deterministic MDP. En route to any state, our path is going to be either bounded by n, or if it's bigger than n, it's infinity because we're actually looping without actually getting to that other place.
Right.
So the most it can be is n, right?
Mm-hmm.
All right. So given that, we might make n mistakes to find out something new, to learn something new, to visit a state action pair that we've never seen before. How many times can that happen? How many times can it be that there's a policy that brings us to a state action pair that we haven't been to before?
How many times can that be?
Yeah. So each time this sort of step 3, maybe I should write it in English. All right. So what this step 3 is that what our Rmax algorithm tells us to do is to execute a path that actually brings us to an unknown state action pair. Then we go traverse that edge, find out what it really is, and generate a new policy. So the number of steps that it might take to get to that new state action pair is n,
Right.
and the number of times that we might discover a new state action pair is what?
N times the number of actions.
N times the number of actions, because that's the total number of unknown things in the graph to begin with.
Right.
Right. So we're exploring the MDP, and each time we visit a state and take an action we haven't taken before, that's going to reduce 1 from the count.
Mm-hmm.
So the largest that count is n times k. And so the total number of mistakes that this algorithm can make is bounded by n squared k.
Hey, that's polynomial in n and k.
It is, and it also doesn't depend on epsilon, and it also doesn't depend on delta.
That's even better. So wait, if it doesn't depend on epsilon and it doesn't depend on delta, then it means it's polynomial in those things.
Sure, yes. It's a very simple polynomial in those things.
So then we're polynomial in everything.
Yeah. So this is an efficient exploration algorithm for deterministic MDPs, right? All it's saying is whenever we don't know something, assume it's awesome, behave accordingly. If we learn something new, make note of it. And so the number of times that we take a step that might not be the best thing to do from that state can't be any bigger than n squared k.
That's beautiful.
Yeah, it's pretty cool. This kind of analysis comes from a paper that Sven Koenig wrote with Reed Simmons, where they actually analyzed Q-learning in this kind of setting, and they got a worse bound, like n cubed times k. But this algorithm is sort of pretty simple, and it gives us a nice bound, and it sort of does what you'd want it to do.
That's cool. I will point out that n cubed k is also polynomial.
Yes, but it's a slightly worse polynomial. You're absolutely right. I mean, he showed that Q-learning has a polynomial bound in these kinds of environments if you set up the rewards correctly and if you set up the initial value functions correctly. All right, so that gets us through stochastic MDPs that have no state and state MDPs that have no stochastic. And the last thing we want to dive into is what happens if we do something like Rmax except for on stochastic MDPs.
Well, we still have another case. We have to worry about the case where we have no state and we have no stochasticity.
So, okay, well, let's do that one really fast.
All right.
So you're talking about an environment that has one state and all the actions are deterministic. They give you a deterministic reward and return you to that state.
Right.
So this is essentially a deterministic bandit problem.
Right.
So how many mistakes might we, well, like what would be an algorithm for this and how many mistakes would it make?
The dumbest one would be, or the simplest one would just be take every action once, and then you know everything.
Right, and each of those, so k minus 1 of those are mistakes, possibly.
Mm-hmm.
And then, when we know that, then we just keep choosing the optimal action thereafter.
Yeah, and you could do a little bit better if you assume that everything was Rmax, because as soon as you come across Rmax, you can stop.
Very good, yes. Right, if you end up finding along the way an action that actually gives you the full value, the full Rmax value, then we don't have to explore the rest of them because they're not going to be any better. Yeah, okay, so that gives us it doesn't give us a better bound, but it does probably give us better performance if we keep track of that. So so this is a silly case.
Well, but it does allow us to do, say we solve 3 of the 4.
Great. All right. So let's dive into number 4. So that's pretty cool. So we have an upper bound that says that our algorithm is not going to take any longer than n squared k steps to explore a deterministic MDP. And a reasonable question to ask is that good or bad? And so what I want to argue next is that there's a lower bound saying that no algorithm can do better than n squared k, and therefore our algorithm's actually doing very well.
Okay. Well as one can do.
As well as one could do, right, which may not be well enough. No, and in fact, really, when you're trying to learn in these kinds of domains, you don't really want to make worst case assumptions. So this is under a worst case assumption where there's really no structure in the MDP. How many mistakes might we make en route to finding the optimal policy?
Okay.
All right, so let me draw a little MDP. So here's an MDP that we can call combination lock. So the basic idea of this is that we've got some kind of end state sequence and two actions, which I drew as purple and blue here. And each state has a purple action and a blue action. And one of them goes back to this reset state, this state number 1, while the other one advances us up the chain one step.
I see.
And so we need to explore this whole thing, say, because there's some kind of giant reward over here, and every step that we're not making along this chain and then looping around here is a mistake. So the question is, how many mistakes might we make en route to finding this plus 100? So let's say we start off in this state number 1. So what would Rmax do in this case, Charles?
It would pick one of them because they look the same.
Right. So it's in this state. It doesn't know anything about the outgoing actions, and it knows that there's purple and blue. So it picks one, and there's really no. I tried to be kind of random about the way that which one would go forward and which one would go backwards. So there's really nothing you can do other than guess. If you guess wrong, then you take this blue action and end up back in state 1. At which point you'd say, okay, well, I know what that does. Let me try the purple action, and now it advances us to the next state.
Right.
All right. So what happens from here?
Well, you don't know what's going to happen next, so you pick one of them.
Right. And so if we choose the purple one, we get reset back to the beginning, at which point we can kind of march up the chain and get back to where we have some unknown information and then try blue. But basically, each time we're exploring one of these states, it's taking us, well, if you think of it as state I, to explore state I, we take one action, which resets us back to the beginning, and it takes us I steps to get back to I, and then one more to get to the new state I plus 1. So the total number of steps that we're taking here is going to be like 1 plus 2 plus 3 plus 4, all the way up to n.
Right. That looks very n-squarish to me.
Which is exactly right, which is n-square-ish, as some people say, right? So this total number of steps that we take, it's not literally n-squared, but it's some constant times n-squared. And you can't really do better than that. Now, in this particular case, we really wanted to prove a lower bound that was going to relate it to k times n-squared, where k is the number of actions. Here, the number of actions was 2. Do you think this same example actually kind of scales up for greater and greater k? How would you change this example so that it would basically force us to do k actions times n-squared?
Well, I can just make all but one of them send you back.
Yeah. Okay, so let's think about what that would do. So if we had k actions, one of them sent us forward and we have no idea which one, and all the other ones send us back to the beginning. Then what's going to happen is we're going to have, each time we explore state I, we're actually going to get reset and have to take n steps k times.
Right.
Right. So for each of the n states, essentially, we're going to have to explore all the actions, and for all but one of them, it's going to be n steps to get back to where we are exploring again. And look at that.
Looks like n-squared k, or k n-squared.
Yeah, I just reordered it so that it looked more like the thing on the top.
If you remember from our last machine learning class, everything got us back to k and n. And there you go.
Oh, nice.
It's all the same.
It's always k nearest neighbors, but in this case, it's not.
It's k farthest neighbors.
No. Well, yeah, I guess there's some truth to that each time we take an action that we don't know about, we're getting unlucky, and we're having to take a very long trail to get back to where we started. But no, I'm just saying k nearest neighbors is a particular kind of algorithm, and here we're just talking, n doesn't stand for neighbor here, right? It stands for number of states.
I prefer to think that n stands for neighbor in this case.
Great. Okay, then I think we've got this one under control. So that's the argument that I wanted to make there, is that that we really do have to take k n squared in the worst case in a deterministic MDP to figure out what's going on and stop making mistakes.
Yeah, and there's no way around it because this is like it really is a combination lock. The way you draw it, it's a random binary string that gets you to the end. Unless you get extremely lucky, there's no way to figure out what it is without trying all the combinations, sort of.
Well, it's not all the combinations. So combination lock in some ways is actually not a great name here. So in particular, what makes it a combination lock is to make it across this whole chain of n things. You have to choose the right color in sequence. You have to choose, in this case, purple, blue, purple, purple, blue, 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 blue. Right? So you have to kind of crack the lock. In a real combination lock,
right,
if you get any of these wrong, at the end of it, you don't get to find out which ones were right and which ones were wrong. You get reset back to the beginning and you just have to start again. So you really end up taking like number of actions to the number of states.
Right.
Different combinations. Here, we're lucky enough to actually know, hey, the first I parts of our combination are correct, and we're just guessing the ith one.
So really it's a sequential combination lock.
Yeah, which is not very secure from a I don't know, security standpoint.
Well, in particular, you can solve it in squared time instead of k to the n time.
Right. So n squared doesn't sound so bad if you're comparing it to k to the n.
Right.
But anyway, the point is that we can't get around that. And so that's really what I wanted to do. So the next thing I want to talk about is combining this idea with the bandit idea that we talked about earlier and get an algorithm for general MDPs.
Okay.
So we want to do efficient exploration in general stochastic MDPs. And so we're going to need to combine the two ideas that we've been talking about.
Wait, what were the two ideas we were talking about?
Well, in the context of bandits, we talked about stochastic processes, and the trick that we used was to use something like a Hufting bound. We just keep repeating the stochastic thing until we have enough data so that we can make accurate estimates.
Oh, okay.
And then we talked about sequential domains that are deterministic, and the main trick that we used there was this Rmax trick that said if there's a state action pair that we don't know about, assume that it's really, really good.
Okay.
We can put these two ideas together and get a stochastic version of Rmax.
Okay. So we'll have Hufting regions.
Yes.
Good.
We're still going to use Hufting bounds on the individual state action pairs.
Okay.
In fact, regions probably mean state action pairs here.
So I was right.
Yes, you were right.
Good. Well, then I think we're done here.
All right, so let's write down what this algorithm looks like. We're going to make a general Rmax algorithm, and it's going to be really simple because it's going to be an awful lot like the Rmax algorithm we already looked at.
Good.
So I copied over the Rmax algorithm that we had before, and it went like this. We're going to keep track of the MDP, which is to say we're going to have an estimate of the transitions and rewards for all the state action pairs. Any unknown state action pair, we're going to assume has a reward of Rmax and then a self loop so that we can just get like for a long time. Then we build that MDP, we solve that MDP, and we take an action from the optimal policy with respect to that MDP that we solved. The only difference is going to be this notion of unknown. And the idea is that we're going to have some parameter, call it C, that state action pair is unknown if it's been visited or we've tried it out fewer than C times.
Okay. Is that C different for every state action pair?
That's a good question. So I want to first kind of give the parameterized algorithm. Then what we have to do is, if we're going to say that this algorithm is efficient, we have to derive some value for C and show that it's, not too big and not too small, but,
Just right.
Just right, yeah. So the way that we're defining unknown here is that we have some parameter C, and we consider a state action pair SA unknown if it was tried fewer than C times. After that point, then we switch over to the maximum likelihood estimate. So we've tried it C times, and we saw, we went from state S with action A to some state, S53. So if we did that some number of times, if we only did that once, then we're going to estimate a probability of 1 over C for getting that transition. Okay, so this gives us a new estimate of the transitions and rewards based on the data that we've actually gathered. Okay, so I just want to point out that this is the Rmax algorithm we used in the deterministic case, and this very much is related to the Hufting bound estimate we used in the stochastic non-sequential case, in the bandit case. But just grafting the two things together. All right, so there's going to be a couple key ideas to make this work, and one of them is the simulation lemma. The idea of the simulation lemma is that if we have a pretty good estimate of the real MDP, then optimizing our rewards in that estimate is going to be pretty good in the real MDP.
This is a lemma about simulations, not a simulation of a lemma.
That's right. It's not a simulated lemma. It's a lemma about simulation, right? And so the idea is that we've got transitions and rewards that are off by alpha or less, and we want to think about what happens if we adopt some policy pi, like any policy pi. We want to compare the value that we get for following pi in MDP1 that has transition function T1 and reward function R1 to the value that we get, the return that we get for following policy pi in MDP2, which has transition function T2 and reward R2.
Okay.
And if those are going to be near each other, given that T1 is near T2 and R1 is near R2, then that's going to give us the ability to have accurate simulations, right? We can use our model of the MDP to simulate what's going to happen in the real MDP. And just to be concrete, this is what I mean by the transition functions, reward functions not being too different, that we have this value alpha, and if we take the maximum over all state action next state triples, that the probability assigned by transition function T1 and the probability assigned by transition function T2 are not different by more than alpha. And same thing with the rewards.
So that's a little weird.
How so?
Well, because the transition model is probability, so that can't ever be off by more than 1.
Sure.
And the rewards could be like gigantic numbers that could be off by billions.
Sure.
Billions and billions. So it just seems a little weird.
You feel like it should be two different alphas.
Yeah. Alpha T and alpha R. But maybe not.
Yeah, I mean, I didn't want to proliferate variables when we didn't really need to, but you're right. The scale of these could be very different. I mean, a lot of times in the proofs that people use for these kinds of MDPs, they first assume that rewards are actually all in the range 0 to 1 also. Doesn't change the fact that you still might want a different alpha for the two cases, but it does at least get the scale more approximately correct.
Okay, so then without loss of generality, assume that all your rewards are between -1 and 1.
Or 0 and 1.
Or 0 and 1. Why not? Because, it's all the same MDP.
Yeah, they look more like probabilities or something.
Okay, cool. So without loss of generality, assume that your rewards are between 0 and 1, and your transition probabilities, which would have to be, are between 0 and 1, so that we can use the same alpha and everything kind of works out.
Yeah, again, it still might be worth having different alphas, but yeah, you're right. I mean, again, it puts us in the right ballpark.
Okay, so these are ballpark alphas. So this is a ballpark simulation lemma. I'm perfectly fine with that.
That is.
Now we're out of the ballpark. So that's either a vacuum cleaner or a metal detector, or it's a gigantic baseball being knocked out of a park.
Yeah, it was supposed to be a ballpark, but now it looks to me more like some kind of terrible, cruel alien. So I don't know.
With head issues.
Anyway, the point is that it's alpha close to a reasonable picture.
And that's alpha. Okay.
I actually just started going through the process of proving this, and it was an awful lot like stuff that we've already done in terms of taking Bellman equations minus other Bellman equations. So let me just jump to the punchline. So if you push the math all the way through, what you find is that if all the transitions and rewards are alpha close to each other, then the difference in the values that you get for following a policy is going to be no more than G over 1 minus gamma, where G is that alpha, that error amount, plus a discounted version of that error amount times the maximum reward that we get for forever. Right. So this is actually the maximum value that you can get if you get the maximum reward over and over and over and over and over again.
Okay.
So this just gives a quantity, and it has some properties that you'd expect, like the fact that if we estimate the parameters perfectly and alpha is 0, then this is 0 plus 0. And then this is 0 over 1 minus gamma, which is 0. And so the two value functions are actually identical, but they fall off from each other. So if this alpha is something not 0, some slightly bigger than 0, then these value functions are going to be off by a bit more. So ultimately what we're going to want is we want to know how accurately do we have to estimate the transition and rewards? What should alpha be so that the difference between the value that we get by running in our simulation of the model and the value that we get running in the actual MDP are really small, like epsilon close. So I think all we need to do actually is solve for alpha in terms of epsilon to be able to see how accurately we need to do our estimates to make sure that ultimately our values are going to be close.
That makes sense to me.
So this is me now solving for alpha, and we end up with this expression here, which says that we need to take the epsilon that we want, how close we want the values to be, and then transform it in various ways, actually make it a heck of a lot smaller. And that gives us how accurate we need the estimates of the transitions and rewards to be so that we know that we're going to be that close in terms of the value.
Sure, that's intuitively obvious, even to the most casual observer.
Well, okay, you're probably being sarcastic.
Possibly.
So it's maybe not completely obvious, but I did algebra here, so it's not deep, but it's not intuitively obvious to me why it should have exactly this form. In fact, usually, I don't know, epsilons are like 1 over. Oh, but I guess we're trying to define a quantity alpha, which is like an epsilon quantity. So it wouldn't make it sense for it to be a giant number. It should be a tiny, tiny number. But yeah, no, you're right. It's not completely obvious. But the point that I want to make with this is they're polynomially related to each other, right? So if we have Rmax and 1 over 1 minus gamma and 1 over epsilon, then the kind of alpha that we get out is going to be polynomially related to the other things.
Okay.
So that's reassuring. I mean, if you actually work out what these numbers are, they're pretty scary. But we're trying not to let ourselves be scared of that. The important thing, though, is that alpha is not really a parameter of Rmax, the Rmax algorithm, right? What was the parameter that we had when we talked about the algorithm?
Sí.
Excelente.
Buenísimo.
So that is to say, what we want is a parameter that says how many times do we have to try a state-action pair before we are confident that our estimate of that transition probability is better than alpha. So how are we going to get that last piece? How are we going to turn alpha into C?
More algebra?
Yeah, but specifically there's bounds that come into play here. So now we've actually turned it into the same kind of problem as the bandit problems that we were talking about, right? That we need to know how many times do you pull a bandit arm before your estimate in the mean is sufficiently close. And that was the Hufting bound.
Right. You did say we were going to use Hufting bounds.
Yeah. And the union bound.
Oh, yeah.
We want to simultaneously make this alpha close estimate hold across all state action pairs. So we need to make the C big enough so that the probability that it fails in any one of them is sufficiently small. But it really is exactly the same argument that we did when we were talking about bandits.
Okay. And sure. So every state action pair is like a bandit, and you have to pull it a certain number of times.
It's like an estimate of an arm, right? And we need all the arm estimates to be accurate if we want the arm that we eventually pick to be nearly optimal.
Right. Okay. No, that makes that, I can see the analogy. I can see the metaphor. I can see the simile.
All right, perfect. So, okay, there's one more piece to this story, and then I think we're done with exploration.
Hey, we'd be done exploring exploration. That sounded sort of sad.
So the last little piece to talk about is the explore or exploit lemma. So the idea of the explore or exploit lemma is it gives us the piece of the argument that we did when we were doing deterministic RMAX, which basically said if we are in some kind of a loop going around and around and around, then we're getting optimal reward. If not, then we're going to quickly reach an unknown state and we're going to learn something. And so the corresponding version of this in a stochastic domain is, okay, so let's say we're running RMAX, and all the transitions are either accurately estimated or we mark them as unknown, and we have an RMAX transition for those state action pairs. Then, if we take that MDP and optimize it, that optimal policy is either near optimal, in other words, that we're not making any mistakes. The reward that we're getting as we travel along this optimal policy is essentially optimal, or we're actually going to make it to some unknown state, some RMAX marked state, relatively quickly in polynomial number of steps. We're going to reach this new state, and we're going to learn something from that. And so this property ends up being true throughout the execution of RMAX.
I'm sorry, literally that property, or that property like with high probability?
Right, with high probability. Right. So things can always fail. We set up our union bound in such a way to make sure that the probability of failure is sufficiently small. Given that it hasn't failed, then this will actually be true. And if it's true, then what's going to be happening is we're either going to be doing the right thing, or we're going to quickly bump into a new state and learn something new and continue. And the number of times that we can learn something new is going to be bounded by the number of states times the number of actions. And the number of steps before we learn something new is bounded by a polynomial in the various quantities. And that's, I think, all we need, right? So it can't actually run for a very long time without either learning something new or being near optimal.
I feel like there's some metaphor for life here.
How would that go?
I'm not sure. Something about grad school.
Yeah, you can't always just go there.
Oh, I'm pretty sure you can, and I proved it for many years.
All right. Well, so I don't know if this is related to grad school, but it is sort of a key property of these algorithms that's just basically trying to handle the case that says, by virtue of the fact that we make the unknown stuff optimistic, we do the right thing, right? So we're either learning quickly or we're being near optimal. And so what would be bad is if there was some kind of hole in between these two cases, right? That says, well, we're kind of stuck doing something suboptimal for a long time, but we don't know it, and we don't learn that we are doing something wrong. That's the bad case. And what this lemma is about is showing that, in fact, the bad case doesn't happen. That either we're learning something or we're doing very well.
Right, and that could only not happen if we were incredibly and extremely unlucky. But if we were incredibly and extremely unlucky, then you couldn't learn anything anyway.
Yeah, right. That's and that's back to this sort of pack notion that it's probably going to work, and we can actually put
at least approximately.
Yeah, that's right. And working is here related to approximately. So that was really all I wanted to get at with exploring exploration. So this idea that even in general MDPs, we have a way of organizing our learning so that we can make guarantees on how close to optimal we are and how quickly we get there.
But wait a minute, you didn't tell me what C was. Is C just quickly?
Oh, this C is correct.
No, I meant the original C that was a parameter.
Oh, well, I did not write down a formula for that, but it follows the same analysis as what we did when we wrote down the value of C for bandits.
Oh, okay.
So good enough? We could make that a homework problem.
Sure. I mean, that's what we usually do. I don't want to write something down. Okay.
All right, done. So what did we learn about exploring exploration, Charles?
Well, we actually learned a lot, but really I think you can summarize in just a couple of things. We learned about bandits,
Okay.
which is really all about stochasticity and randomness. And in particular, we learned about how we can estimate what we know using Hufting bounds and maybe some union bounds.
So yeah, in particular, we employed Hufting bound, union bound to convince ourselves that we have a sufficiently accurate estimate that we can get near optimal reward in these kind of non-sequential but stochastic decision problems.
Right, and that's really important because a lot of the time you don't know what to do because you're not certain or how certain you really are about what you know. And what the Hufting and union bounds tell us is how certain we really are, and so we can know when we're certain enough.
Good. All right, so we have a stochastic world. We want to learn how it works so that we can get near optimal reward, so we can optimize.
Right. So that was the first thing. And then the second thing is we learned about RMAX, really, and how RMAX works specifically with deterministic MDPs.
Right, and so that was about optimism in the face of uncertainty and how it would cause us to explore or discover new stuff about the world kind of by planning ahead and trying to get to states where new information could be gained.
Right. Well, what it really says, it's really, we believe the grass is always greener until we get there and learn otherwise.
All right, great. This let us deal with sequential decision-making. This let us deal with stochastic decision-making.
And then we combine them.
Right, where we used the bandit idea to estimate the noisy parameters, the transition probabilities and so forth. And we used the RMAX idea to make sure that we visited things enough so that we could get those accurate estimates.
Right. So RMAX still basically remained RMAX. And the bandit stuff helped us with the transition probabilities so that we knew when we actually believed them. So they were kind of, I mean, this isn't really true, but they were kind of deterministic enough. So we knew enough to know what the transition model is. And once you know what the transition model is, you can just kind of go from there. Because then you can just estimate the rewards and do the right thing.
Now, this notion of the way that learning happens in the bandit here, where we actually kind of distinguish between known and unknown, can actually be generalized even beyond the kind of general MDPs that we're talking about here. And I don't think we're going to get a chance to talk about this, but the idea of quick learning is learning transition probabilities using methods that know what they know. And if it can distinguish between known and unknown, it can associate optimism with the unknown, and then we can make guarantees on how quickly and efficiently near optimal behavior can be learned.
Nice.
So this is kind of a learning framework that my students and I have been studying to try to generalize beyond learning in tabular MDPs to be able to generalize between transition probabilities in different parts of the MDP.
Well, that all makes sense to me. So then the only question is, how does this help us do practical reinforcement learning?
All right, so that pretty much ends this. Well, so just briefly, I find that RMAX is actually a really effective algorithm to use in practice. We don't set that parameter of how often we need to see things to be what the theory says we should set it to. We usually set it to something much, much smaller than that. And we try to, by hand, strike a trade-off between making it too small, in which case it might actually not learn near optimal behavior, and making it too big, in which case the learner actually has to sniff around and visit many state action pairs over and over again. So RMAX itself does seem to be a pretty effective algorithm. It makes very good use of the data. It's just we can't quite use it in the theoretically specified way.
Okay, well, that's good enough for me. Seems pretty practical. Okay, so we're done. So are we done with the class? What's next?
We have more stuff. We have what's next.
Oh, cool. Well, I look forward to that.